Hello scientists, this is Miss R and we're going to talk about Lab 407, Shapes and Fluid Forces. I will let you read the science standards and learning goals. Our first job is to go here and kind of play with the simulation a bit to see how it works. We're going to look at the plot curl, that's the blue and yellow swirls behind the barrier. We'll see what that looks like in a minute. We're going to think about viscosity, kind of the goopiness or how well something flows. We're going to talk about the change of viscosity and what happens when you change the viscosity of the fluid in the simulation. We're going to change the flow speed. That's how fast the liquid flows or the fluid flows past the object. And what barrier shapes cause the most plot curl. And you'll see what I mean by plot curl in a second. What we're doing here basically is seeing how well things can be pushed through fluid. Here's my mouse here, and that's pretty aerodynamic or fluid dynamic. If we try to push my mouse through some fluid or air fluid or watery fluid, it would probably be a pretty good shape to push. But if you push like a more blocky shape, like say the tape dispenser here, this is going to provide a lot of air resistance. So let's think a little bit more scientifically about this and go look at a simulation. So using the URL on your lab sheet, you can get to this simulation, and it first looks pretty darn boring. But I actually have mine on pause. You will have to set it to run. We'll have to put a barrier in there, so we can put, let's just put a big blocky shape in there, like a short line. And then we can say run. And this is what I'm talking about plot curl. What's happening to the fluid? Is the air or liquid disturbed after it goes by whatever you're sort of driving through the fluid? And you can see, like if you drive a big honkin' semi or something that's very square, like our barrier here, this is kind of the top view of us driving a big square thing through some air or some water. Maybe it's a big square barge. It's not a particularly efficient shape. We can use some other shapes here. We'll clear this one by pressing clear barriers. Oh, that one just disappears. Let's try something else. Maybe we can cut through the air with a diagonal line a little bit better. We still see some big chunky plot curl here. Let's try a different shape. How about a circle? We still see some pretty chunky, turbid air here. If you've ever kind of felt a car go by, you can kind of feel the swirling air behind it. Let's see if we can get something that's a little bit less swirly. Let's try a spoiler. A spoiler tries to kind of even out the air as it passes over the front of the car. You might have seen one of those little things on someone's trunk that's trying to kind of control the air as it flows over the car and leaves the car. And that looks like it smooths out the air pretty well. Spoiler works. Imagine that. That's why they put them on cars, the sportier cars. Let's try a circle with a spoiler. That looks pretty good too. How about a right angle? Not too bad. As long as you put this spoiler on here, it kind of calms down the turbulence behind the object. Do a wedge. That looks pretty good. An airfoil, like an airplane wing. This is a cross section of an airplane wing. That seems to be working pretty well. An airplane should be pretty aerodynamic because they fly through the air. That makes sense. Okay, let's hit pause and play with some of the other buttons. We can reset the fluid. We can change the viscosity or like the thickness. One way to think about viscosity is like pouring molasses. It's really thick, it flows slowly. That's highly viscous. Molasses is viscous. Whereas if you pour a glass of water that pours quickly, that's less viscous. So molasses, more viscous, water, less viscous. So let's up the viscosity here. And let's keep the flow speed the same because we're doing an experiment. We only want to change one thing. And let's run it again. So we increase the viscosity quite a bit. You can kind of see it looks like everything's kind of slowing down here. It looks like there's not even a whole lot of flow back here. Let's pause it for a second. Let's put in our original very chunky little line here and see if we get the same kind of turbulence we did with that original barrier line. And it turns out it looks like viscosity, the relationship between viscosity and turbulence, the more viscous something is, it looks like there might be a little less turbulence because there's less opportunity to flow and create turbulence. Let's pause here. So we changed the viscosity. Let's bring the viscosity back down. Well, we've got it paused. So about what we had. And let's turn down the flow speed. So it's pretty viscous. Or it flows pretty quickly. It's not too viscous. It flows pretty quickly, but the flow speed is going to be different. Let's see how that changes things. Oh, wow. Yeah. Let's just mess around with that a little bit. So the more you up the speed, it looks like the more turbulence you might get. Let's wait a second. Sometimes it takes turbulence a minute to develop. Oh yeah, we can see it kind of getting messed up here. Now you can see the air getting all washed out and weird, which makes sense because race cars, like Formula One cars, are designed a little bit differently than, let's say, your suburban minivan that's just going to, putt along at 55 miles an hour. So if you change the flow speed, like you're going to drive your car faster, or maybe the wind is blowing faster on your car, the turbulence is going to increase. So let's go back to the lab sheet here and look at what you need to know. What are the differences in the plot curl, those swirly lines, between a long and short barrier? Well, you have the tools, you know what to do, you know how to change the barriers to figure this out. Viscosity, we've talked about a little bit. It's how quickly a fluid flows. Molasses would be more viscous. It would flow more slowly, and water would be less viscous. If you change the viscosity without changing the type of barrier, how does changing the viscosity affect the swirls? So keep the same barrier, change the viscosity, see what happens. Use the same barrier, change the flow speed. Remember, that's the little dial on the left, the little button, little slider button on the left in the simulation under the green box. Try all the barrier shapes and see what causes the most plot curl. And I know that's a little bit, you have to be a little bit subjective here, but do your best. See what you think causes the most turbulent air behind that shape. Where is the air just swirling up the most? And then think about what real life situations would this simulator be useful. Engineers do a lot of simulations. They try to test things in the lab. Either they build scale models or they use computers to simulate things. What kinds of things could they use this simulator for? We looked a little bit at how the spoiler affects the plot curl. Let's go look at the tracer function and figure out how that is useful. And while we're doing that, why don't you keep in mind, if you're in charge of designing a fuel-efficient semi-trailer, so we talked about how this kind of looks like a semi-trailer. We're driving a big square through the air. How could you use this model to help you in the design process? So let's go look at the tracer function briefly. So here we are, we have our little short barrier here. It's got a high flow speed. Let's turn that down a little bit. Well, maybe let's turn it up a little bit so we can see things. Now, if we put tracers in, here, I'm down here under animation speed where it says show. I can hit tracers. Those are like little, they simulate particles of air, and you can basically see kind of how messed up, what happens to the air in a particular area. And you can see it kind of goes, it follows the plot curls. These particles go up and down, following these wavy lines. You can also look at flow lines. The question doesn't ask about flow lines, but it's interesting to kind of see where the air gets messed up. These are similar to the little smoke lines. If you've seen someone in an air tunnel, maybe on TV, they have little smoke lines going through the air tunnel, and this is where the smoke would get broken up. You can also use this, it's called force on barriers, and it shows the vector of how the fluid is pushing on this particular barrier. So this is how tracers work, and you can think about that a little bit more. So part 2 of the lab asks you to do some engineering tasks. Use what you've learned using the model to pick at least 2 design challenges from these 5 potential design challenges below. So you only have to do 2 of these. You don't have to do all of them. Take a deep breath. But I will demonstrate how you might use the draw barrier feature to take on some of these challenges. The first challenge is a semi-trailer, boats, a house, and where the snow might accumulate behind the house. So kind of thinking like if you live out on the prairie where the wind just blows and blows and blows, where should you put your house to keep snow from piling up against it? You could design a snow fence for an area in your community. You could draw an island in a river to figure out where the trash or flood debris might accumulate around the island. So if you're kind of planning your dream home on an island or a resort or something, you're an architect, you don't want to put something where a whole bunch of flood debris is probably going to accumulate. There's another one that I wanted to add. If you want to do this one, just call it number 10.5. You can also design a house that survives hurricanes if you'd like to. That's a little less applicable for Minnesota, but if you've lived somewhere or want to live somewhere where there might be hurricanes or you have relatives in a hurricane zone, that is something you could think about as well. So let's go figure out how to do the draw barrier. So to clean everything up, I hit reset fluid, I hit pause, it was running, now it just says run, and I hit clear barriers, that tidies everything up. Now if I want to draw barriers, I can just take and draw a hill here. Let's see how that works. Let's run that. Well, it's gonna draw, that's why you should draw your hill at the bottom or your house at the bottom. That's pretty telling. Let's clean everything up here. Okay, so let's draw a house here at the bottom. It's not a great house, but I'm sure you can do better. So where do you think the snow would accumulate, and how could you keep it from accumulating? Let's clear barriers here. Let's draw a semi. This is basically what a semi looks like to the air. I probably could do a little bit better job of drawing those lines. I'm sure you will. But think about what kinds of things you could do to a semi. How could you change the shape of the semi to make it a little bit more fluid dynamic, aerodynamic? We don't often drive our semis through water or corn syrup or molasses. We usually drive them through air, so they'll be aerodynamic. We want our boats to be hydrodynamic. So if you want to draw a boat, you might want to think about what shapes boats usually are, and how they move through the water, so that you want to be hydrodynamic and be smoothly flow through the water. We have a little bit of turbulence on this design. What could we do to fix that? So now you know how to use draw barriers. You just use your mouse, you draw a shape, and the simulation will show you how the fluid will move around it and where the turbulence is. So now you know how to do just about all of the lab. Part 3 is a writing wrap-up, where you need to think about the advantages and disadvantages of using a model when designing a product or testing a hypothesis. Obviously, models are not real life, but real life, to build a big boat or even to build a model would cost time and money. So those are some things to talk about. 3 complete sentences, what you learned. What happens when there's friction? When fluid meets friction on the side of an object? What happens as fluid goes past an object? Does it continue in a smooth stream, or what's going on there? So 2 points a sentence. Make sure you write 3 complete sentences. Thanks so much, guys. I'm sure you're going to do great on this lab. I look forward to grading them. Bye-bye. This is Miss R signing off on Lab 4.07.